Hello, in this series of videos, I'm going to go over single variable advanced calculus. This would be a proof-based class. And what we're going to do is we're going to present a rigorous analysis of single variable calculus concepts, including sequences, limits, continuous functions, differentiable functions, applications of derivatives, integration, Taylor polynomials, series, and sequences of functions. The way you want to think about this is it's a combination of single variable calculus, whether you have taken AP Calculus A, B, and BC in high school, or you have taken Calculus 1 and 2 in college. A combination of those courses with introduction to proof. So in other words, what we're going to do is we're going to carefully examine all of the things that you have learned in single variable calculus and prove those theorems, things of the sort like intermediate value theorem, mean value theorem, all of the things that you have learned, techniques that you have learned in single variable calculus. We're going to examine them, and we are going to talk about why what you have learned in single variable calculus is in fact true. So the emphasis of the course will be on proving the results. In all exercises and examples, or nearly all of them, you will be asked to prove something. The focus is on making sure that not only you get the correct answer, but also you present a complete proof for all of your claims. So if you're claiming something is true, you need to state why it is true. The main prereq for the course is familiarity with the language of mathematics. Of course, I expect students in this class to be familiar with single variable calculus. But that's a lower level class. But I also expect the students to be very comfortable with language of mathematics, how to write down a complete proof. And what I'm going to do today is I'm going to go over some of the basics of that to see if you are ready for this class. There are some digital notes for this class that can be found on Google Drive, and the link is posted in the description, and I'm going to also, I have also posted the link here. So what I'm going to do now is go over first how to use these notes, then go over a diagnostic test, and then we'll talk a little bit about how to write down proofs. And this would be a good class for you to know if this is the right series of videos for you or not. So first of all, how do we use the notes, these digital notes that I have posted on Google Drive? The first thing you want to do is to start with the diagnostic test. So make sure you are comfortable with the material in the diagnostic test. Read the proof writing section of the notes and make sure you're comfortable with writing proofs. I would say if you get 85% or above in the diagnostic test, you should be ready for this class. In your first reading, you can skip chapter 0 or the preliminaries. And at a later time, you might have to come back to the chapter 0 to make sure you are in fact ready and haven't forgotten anything about properties of real numbers and methods of proof. Each section would have 4 different types of problems. There are warm-ups, there are examples, exercises, and challenge problems. Warm-ups are very basic problems, and everybody who gets like a basic understanding of the topic in each section should be able to do those problems. And all of those have solutions in the digital notes that I have posted. Examples are solutions that are more common in this class. They're a little bit more complicated, but not very complicated. And all of those also have solutions. There are some exercises that are problems without solutions and some challenge problems. The challenge problems are for the ones who want to get more out of this class. Make sure you do not also miss the summary of each section. It runs you through what is needed for you to learn in this what is needed for you to be able to do the problems that are the type of problems that you should be able to do in each section. Proofs of most of the theorems are omitted in the notes. However, I will go over many of the proofs in these videos for this class. Some of the proofs are, most of the proofs, and in fact, perhaps all of the proofs are also in the textbook. And you can also consult the textbook, which is Advanced Calculus, second edition by Patrick Fitzpatrick. Okay. So before you get started with the course, you want to see if you are ready for this class. What I would suggest is for you to pause the video at this point, go over the diagnostic test on your own, make sure you score 85% or above. If you score below that, you would need to either revisit and refresh your memory of the things that you have learned in an introduction to proof class, or if you haven't taken that class, you may want to consider taking that class before doing Advanced Calculus 1. Okay, so I would suggest that you pause the video at this point, go over the diagnostic test, which is inside the digital notes that I posted, and come back when you are done. Okay, welcome back. So what we're going to do now is we are going to go over the diagnostic test, and then we'll talk about some of the common errors in writing down proofs. Okay, so the first thing we want to do is we want to negate each of the following statements. So the first part is there is a real number x for which x squared plus x minus 5 is less than 10. So the statement is an existential statement, and we want to negate that. The negation of that exists becomes for every. So it becomes for every real number x, and then I have to negate this one. X squared plus x minus 5 is greater than or equal to 10. So the negation of for every is there exists, and then you have to negate what follows. This one is a universal statement. In other words, it says for all positive real number x. So when we negate that, it becomes there exists. So there exists a positive real, and this is how I show positive reals, such that x to the power of x over x plus 1 is irrational. And we have to negate that, so we have to do not irrational, which means it is rational. The next part is the sum of every two rational numbers is rational. So I think I'm going to move that down here. Since, again, the statement is a universal statement, I will have to negate that. So there are two rational numbers such that their sum is irrational. And this is how I show the set of irrationals, the complement of rationals. So again, because the statement is for every, we negate that, and then we have to negate rational as well. The next one is the product of any rational number and any irrational number is irrational. So negating that, again, because it's universal, we'll have to turn that into existential. So there exists some x rational, and there exists some y irrational, such that x times y is irrational, but we'll have to change it to rational. So again, for every becomes there exists, and irrational becomes rational. Part E. For all real numbers, that becomes again for there exists. So there exists a real number x such that. So the statement is an or statement. So we will have to change this to and statement. So it becomes negating that becomes x is less than or equal to 1 and x squared minus x minus 5 minus 1 is greater than or equal to 0. And I also would put parentheses to make sure it is not ambiguous. So negation of greater than becomes less than or equal to, and negation of or becomes and. Okay, part F, there is a positive real number x for which x and x to the x are both irrational. So again, this is there exists, so it becomes for every. For every positive real number x. So the statement is x is irrational and x to the x is irrational. So what we have to do is we have to negate that. So negation would be x is rational or x to the x is rational. So negation of and is or, negation of irrational is rational. And finally, for every epsilon positive, so we'll have to go through that. There's a lot of quantifiers here. For every becomes there exists. And that becomes there exists epsilon positive such that the negation of there is becomes for every natural number n. Negation of for every integer n becomes there exists an integer n greater than or equal to n. And then negation of sign, absolute value of sign less than or equal to epsilon is absolute value of sign is greater than or equal to epsilon. So again, for every epsilon positive becomes there is epsilon positive. There is n in n becomes for every n in n. For every integer n becomes there is an integer n. And then absolute value of sign less than epsilon is absolute value of sign greater than or equal to epsilon. So that is the second problem of this, the first problem of this diagnostic test. Okay, and this is 7 parts, so there would be 35 points for this one. Okay, so we're going to go over problem number 2. This one is about proving or disproving each statement. So this one says you have to present a proof for each one of these. This is not just simply saying what's the negation, but it is saying, is this statement true or is its negation true, or is this statement false, in fact? So what we are going to have to do is understand each of the statements, and in the context, we have to provide either a proof or a counterexample. So let's look at the first one. The first one is there is a positive integer n for which n squared is less than 5. So all it asks us to do is to say, is there a positive integer n that n squared is less than 1? If there is one, then the answer would be it is true. And clearly we know that there is such an n. This one is an existential statement. It says there is. So all we need to do is to provide an example. So n equals 1 satisfies n squared less than 5. We do not need to provide 2, 3, 5 examples. Only one example is enough. And in this case, we have only 2 examples. N equals 1 works and n equals 2 also works. But we don't need to provide both of them. Only one of them is enough. Okay. The second part is for every integer n, 2 to the n is less than n to the 4th. So if you think about this one, the left-hand side is an exponential function. The right-hand side is polynomial. From your experience, you know that exponentials grow faster than polynomial. In other words, 2 to the n at some point is going to be more than n to the 4th. So we're going to just try something large. So this one is false. All we need to do is give one counterexample. So n equals, let's say 100 is a counterexample. So for this problem, we only need to provide one counterexample. And of course, we need to specify why this counterexample works. So 2 to the 100 is equal to 1024. 2 to the 10 is 1024 to the 10. And this is greater than 100 to the 4. And this comes from properties of inequalities, because 1024 is more than 4 and 10 is more than, 1024 is more than 100, and 10 is more than 4. So this one is false. Any of these statements that they're asking us to prove or disprove, you have to first state, is it true, is it false? So state it is true, it is a state it is false, and then provide a proof or a counterexample. Depending on the situation, your proof could be short or long, or it could be just referring to a theorem. Okay, part C. The product of any non-zero rational number and any rational number and any irrational number is irrational. So if you take a non-zero rational, multiply it by an irrational, you get irrational. From your experience, you know that it is true. If you take, say, 3/5 multiplied by √2, you get 3/5 √2, and that is an irrational number. So this is true. And we're gonna take a rational number. So assume X is rational and non-zero, and Y is irrational. Now, we are trying to prove that the product is irrational. In order to prove it's irrational, we have to prove it is not rational. In order to prove something is not rational, we will use proof by contradiction. So you can either say we will use proof by contradiction or specify that on the contrary, what assumption we make. So on the contrary, assume XY is rational. So by definition, X is rational, so X is M over A, and XY is rational, so XY is N over B for some MN AB integer with A and B non-zero. Now we're going to evaluate Y from here. So in order to evaluate Y, we need to divide by X. So since X is non-zero, Y becomes N over BX. And if I substitute X in here, I get NA over BM. Now note that the numerator and denominator, NA and BM, are integers, and BM is not zero, since B and M aren't zero. And this is since X isn't zero. Thus, Y would be rational. And this is a contradiction. Because we assumed that Y is irrational. So if you go back, we had assumed that Y is irrational, and we ended up getting that Y is rational. So these two are contradictory. Okay, so this is a proof by contradiction example, now part C. Part D is the sum of every two rational numbers is rational. So if you take two rational numbers, then their sum is rational. And you know that is true by just the idea of taking the common denominator. So suppose, again, we're going to state that this is true. Anytime you're proving or disproving, you state it is true or false. Suppose X and Y are rational. By definition, X would be M over A, Y would be N over B for some integers M and A B with non-zero denominators. Then we are going to add them up. We're going to get MB plus NA as the numerator and AB as the denominator. Note that MB plus NA is an integer and AB is a non-zero integer since A and B are not zero. Thus, X plus Y is rational. So this one is a direct proof, because what we did is we started with two rational numbers. X is rational, Y is rational. We added them up, and then we showed that their sum is also rational. Okay, so this is a direct proof. The last part of this problem is for every integer n greater than or equal to 4, 2 to the n is greater than or equal to n squared. If you think about this for a moment and try a few examples, you can try n and then compare 2 to the n with n squared. n4 gives you 16 here, 16 here. 5 gives you 32, 25. 6 gives you 64, 36, and so on. 7 gives you 128, 49. As you see, clearly 2 to the n is larger than n squared. But of course, we have to prove that. Since this is stated as for every integer, we can prove that by induction. So first of all, this is true. And then we will prove that by induction. In order to prove it by induction, we will have to take the basis step, prove the basis step. Basis step is for n equals 4. Because they said starting from n equals 4, it is true. So n equals 4, 2 to the 4 is 16, which is greater than or equal to 4 squared, because that's also 16. Now inductive step. For inductive step, what we need to do is we would have to assume it is true for n and then prove it for n plus 1. So suppose n 2 to the n is greater than or equal to n squared for some n greater than or equal to 4. Now, if you multiply both sides by 2, we get 2 to the n plus 1 is 2 times 2 to the n greater than or equal to 2n squared. We would like to show that this is greater than or equal to n plus 1 squared. So we're going to create n plus 1 squared. And this is greater than or equal to n squared plus 4n, which is n squared plus 2n plus 2n, which is greater than or equal to n squared plus 2n plus 1. Because 2n is more than 1, and that is n plus 1 squared. So this means 2 to the n plus 1 is greater than or equal to n plus 1 squared. And that completes the proof. We showed that it is true for n equals 4, and then we assumed it is true for n, and then we proved that it is also true for if n implies n plus 1. Okay. So this second problem had 5 parts. So this would be 25 points. So far, 60 points. 60 points for this problem, for these two problems. Okay. To prove this statement, the square of every non-zero real number is positive. Is the following proof correct? So the way they stated the proof is they take a positive integer n, a positive number 2, and then they evaluated 2 squared, which is positive. Then they took one negative number, they squared it, they got another positive number. So that gives you also 4. And therefore, they concluded that the square of every non-zero real number is positive. Clearly, this is false because universal statements, this is a universal statement because they said for every. So universal statements cannot be proved by examples. We can't prove this universal statement for example, by providing examples. So the examples showed that this statement is true for 2, and it's also true for -2, but it did not show it is true for everything else. So this is this is not a valid proof. Okay. The next problem, number 4. Which of the following correctly and completely proves the statement for every epsilon, real number epsilon, there is a natural number n such that epsilon is more than 1 over n? So notice that it is a universal statement followed by a universal quantifier followed by an existential quantifier. So in order to disprove this, you have to provide an example of epsilon and then show that for every, so you have to prove that there is some epsilon that for every n, epsilon is less than or equal to 1 over n. This is what you need to show. If you look at the first one, they did provide a counterexample. This is good, but they only proved it for one n. They didn't prove it for every n. They proved it for one n. So this is not a valid way of providing a counterexample. In the second one, they said something which is like kind of conceptually, it conceptually makes sense, but it is also not a valid proof because they didn't provide a specific example of epsilon that violates the statement. So they have to provide an explicit example of epsilon and then show that in fact it violates the epsilon greater than 1 over n. And that is fixed in the last part, which is they provided an example, epsilon equals -1, and then they showed that -1 cannot be more than 1 over n. Because if it is, they got a contradiction. Okay, so that is for problem 4, part C. Problem 5. Is the following proof correct for the statement for all positive integers n, 2 to the n is greater than n? So the way they proved that is they said, we noticed that 2 to the n is exponential, which is correct, and n is linear. We know exponential grows faster than linear, therefore 2 to the n is greater than n. This is not valid because we need to prove for every n this inequality holds. Growing faster talks about end behavior of the function. It doesn't talk about what happens at the beginning. So the statement must be proved for all n, for every positive integer n. Okay. Next one. Are these true or false? If you look at the first one, they basically factored ai. This is not true because the right-hand side depends on I, which is a dummy variable. It doesn't even make sense. What is written on the right doesn't even make sense. So this is false. Part B is called a telescoping sum. And this one is in fact true. And the reason is this: if you write down sum of ai minus 1, you see this is I equals 1 to n. This is a1 minus a0 plus a2 minus a1 plus an minus 1, which is equal to a1 all the way to an minus a0 all the way to an minus 1. So if you see, the only thing that does not cancel from the first parentheses is an. The only thing that doesn't cancel from the second parentheses is a0. And that's why the equality holds. The next part is also true because both are the sum of a1 through an. So those are both the same sums. I and j are called dummy variables, so they don't actually matter. And the last one is also true because of commutativity of addition and associativity of addition. Okay, so we're going to move on to the last problem of this diagnostic test. So they told us that if you take two sets, set A, I'm going to look at the Venn diagram of this, and set B, set A, which is inside set B, then compare minimum of A, maximum of A, minimum of B, and maximum of B. So if you look at minimum of B, it could be here, which would mean minimum of B would be more than everything in A. So therefore, minimum of B would be less than or equal to minimum of A. And maximum of B would be greater than or equal to maximum of A, because maximum of B is larger than or equal to everything in B, including everything in A. So we claim that minimum of B is less than or equal to minimum of A. And the reason is this: minimum of A is an element of B, since A is a subset of B. By definition, minimum of B is less than or equal to minimum of A. Similarly, maximum of A is inside B. Thus, maximum of A is less than or equal to maximum of B. And therefore, we get what we want. Minimum of B is less than or equal to minimum of A, which is less than or equal to maximum of A, which is less than or equal to maximum of B. Okay. The last thing I'm going to talk about today is about writing mathematics. Some of the things you want to watch for when you're writing down a proof. Okay, so here are a few things you want to keep in mind. When you're writing down a theorem or a definition, which is very critical for learning how to write down proofs, how to learn the language of mathematics, is the first thing is use proper English. It is perfectly fine to use mathematical symbols, use or just words, English words. However, you have to make sure whatever you're writing is grammatically correct. One thing you want to avoid is using pronouns as much as possible. In fact, I would encourage you to not use pronouns at all, at least at the beginning. And here is the reason. If you are saying at some point, you are saying it is positive, that is completely ambiguous, because there might be multiple variables. You have X, you have Y, you have Z, you have N. And then when you're referring to something by it, it's not clear, are you referring to X or Y or Z or N? Now, there are cases that using pronouns is okay and not ambiguous, but it is best to avoid it as much as possible. If you want to use mathematical symbols or you're more comfortable with them, use those. If you're less comfortable with them, you can start with using English words and then slowly learn how to use the symbols. But you are expected to be able to use symbols and, of course, be able to read them and understand them. The second thing is to keep in mind is clearly specify your assumptions and conclusions. If you are writing down a theorem, you have to specify what is the assumption and what is the conclusion. So here is an example. A proper way of stating the intermediate value theorem. This let indicates that you're looking at assumptions. F from AB to R be a continuous function and C be a number between f of A and f of B. So this was, all of that is assumption. So all of these are assumption. And then we indicate the conclusion by then. Then there is, so this would be the conclusion. There is X in AB such that f of X is equal to C. So this is a proper way of stating the intermediate value theorem. Here are a couple of examples that I have seen when I have given exams. So f from AB to R is a continuous function, and C is between f of A and f of B. It is unclear whether this statement that they have is part of the assumption or part of the conclusion. When you say f from AB to R is a continuous function, what does it mean? Are you saying we conclude this is a continuous function, or are we saying this is assumed to be a continuous function? So it is unclear. And then same thing for the conclusion. There is X in AB such that f of X is equal to C. It's not clear whether that's part of the assumption or that's part of the conclusion. And the third example is another way of writing down the intermediate value theorem, which is also incorrect. And that is, again, f from AB to R continuous. This is even more unclear. Is it continuous or is it not continuous? Because there is no verb here. This is like, even grammatically, this is not correct. And again, C between f of A and f of B. It's not clear. Is C between f of A and f of B, or are you saying C is not between f of A and f of B? So you have to make sure it is completely clear, mathematically, grammatically correct, and also mathematically correct, which means you are stating what is assumption, what is conclusion. And then the next part, which is supposed to be the conclusion, but again, it's not stated, is that x in AB such that f of x is equal to C. So you have to state that this is part of the conclusion. Next thing you want to watch for is you want to introduce all of your variables. So if you are using a new variable, introduce it. Say x, and then what is this x? Is it a real number? Is it an integer? Is it a set? Is it a function? What is it? So here is an example. Proper statement of the definition of even. An integer n is called even if n equals 2k for some integer k. So I specified exactly what k is. This k, which is a new variable, is an integer. This k is an integer, and also it is for some integer. In other words, this k is not every k. This k is a particular k. This k is part of an existential statement. Improper way would be to say n is even when n is equal to 2k without stating this k exists and this k is an integer, because otherwise every number would be in fact even, because for example 1 is 2 times 1/2 and they didn't specify k as an integer, so 2 times 1/2 would also be considered as even. Another thing you want to keep in mind is do not include unnecessary assumptions. Oftentimes, students think that the longer, the better, and that's not true. It doesn't necessarily make your solution or statement of the theorem or definition better when you make it longer. It just means you made it longer. That's all it means. So here's an example. A theorem states that let n be an even integer, then n plus 1 is odd. So this is perfectly fine. If n is even, then n plus 1 is odd. Here is a longer version of the same theorem, which made it in fact not a proper way of stating the theorem. Let n be an even integer, so that's fine. That is a multiple of 2. This is not part of the assumption, because saying it's even, it just is also the same as saying it's a multiple of 2. So that's redundant. So you don't want to include that. Then n plus 1 is odd. And finally, watch for the order of your quantifiers for every and there exists. So it's very important to watch for those. So here's an example. For every x in R, there is a y in R such that x plus y is 0. This is clearly true. So if you take your x equals, say, 5, then y would be -5. So for x equals 5, there is a y, and y equals -5 works. So in other words, if you take some x, then y equals -x works. So this is a true statement. But watch what happens when you switch the order of quantifiers. If you change the order of quantifiers, you get there exists y in R such that for every x in R, x plus y is equal to 0. And that's clearly false. There is no one single y that x plus y is 0 for every x, because this x would only work for when x is equal to -y. So this statement is false, because if you have x equals 1, you would need y to be -1. If you have x equals 2, you would need y to be -2. And of course, y cannot be both -1 and -2, because the statement is there is a y, there is a single y. So this single y should work for all values of x, which of course there is no single y that works for all values of x. Okay, so we are coming to the end of this video. If you would like to continue with this, with the subject of proof writing in single variable calculus, and you are interested in learning, feel free to subscribe to the channel. And I will see you in the next video.